This video is on gas law stoichiometry. It combines what we learned about stoichiometry, so quantities in a chemical reaction, with the ideal gas law. So if you remember from before, we learned that 1 mole is 22.7 decimeters cubed. That's only true, though, for gases at STP, so that's standard temperature and pressure. Now, we're still talking about gases in this chapter, but our gases are not always at standard temperature and pressure. There's sometimes different temperatures, different pressures, which is going to affect your volume per mole. So what do we do when it's not at STP? Well, we're still going to use stoichiometry. But we're also going to use the ideal gas law to take into account our different pressure and our different temperature. So let's do an example to practice this. So when you're looking at a problem like this, calculate the volume of hydrogen produced at 0.75 atm and 28.5 degrees Celsius by the reaction of 30 grams of magnesium with excess hydrochloric acid. You need to first have a balanced equation. So I'm going to write some steps over here on the side. So number 1 would be balanced equation. Alright, so let's see. I have hydrogen, hydrochloric acid, and magnesium. And it says magnesium reacting with excess hydrochloric acid. So I've got magnesium plus hydrochloric acid would be HCl. And it's making hydrogen. Hydrogen is produced, it says. Hydrogen is diatomic. And this is single replacement, so hydrogen and magnesium switch places. Magnesium will go with chlorine. Magnesium's plus 2, chlorine's minus 1, so MgCl2. So to balance this, I need a 2 in front of the HCl. So now I want to look at my knowns and my unknowns. So let's see, calculate the volume. So there's my unknown of hydrogen. So under the hydrogen, I'm going to put a question mark, and I'm going to put volume units. Because it doesn't specify, I'm going to use it in decimeters cubed, because that's what my equation and everything will give me. Now, the other numbers given are pressures and temperatures, and those aren't going to be in the stoichiometry part. They're going to go with your ideal gas law when you get to that point. Okay? And then our other number is 30 grams of magnesium. So under magnesium, 30.0 grams. So like before when doing stoichiometry problems, we would start with what we know. I know 30 grams. And I can go grams to moles for magnesium, do that calculation. Then I can go moles to moles of hydrogen. Looks familiar. Okay, but what we used to do is this step, and we used to use that 22.7. The problem is we don't have standard temperature and pressure. We have this pressure and this temperature. So this part can't happen like that. So we're actually going to stop our problem right here. And to calculate this piece, we're going to have to use the ideal gas law. So we will have pressure from here. We will have temperature from here. We always know R. And our moles is going to come from our stoichiometry. That will allow us to solve for the volume. All right, so our next step is to actually do the stoichiometry. So step 2 is the stoichiometry. I'm just going to write stoich for you. All right, so I start with 30.0 grams magnesium. First convert it to moles of magnesium, so grams of magnesium to cancel. Moles is my conversion. And I look on the periodic table, magnesium is 24.31. So grams of magnesium divide out, and I can keep going, because I need to find moles of hydrogen. So moles of magnesium will cancel on the bottom, moles of H2 on the top, and the ratio, looking up at my coefficients, is 1 to 1. So my moles of magnesium divide out. So typing this in my calculator, 30.0 grams divided by 24.31 grams will give me 1.23 moles of H2. Now we have all the pieces except for the one unknown that A, or that V, sorry, to use our ideal gas law. So our third step is going to be using PV equals nRT. Now, quick side note, it is possible that these two steps could be in reverse order. You might have to use the ideal gas law to calculate moles and then do that in a stoichiometry problem. All right, so if I list out my variables, right, I have 1.23 moles. Okay, I go back up to my problem, my pressure is 0.75 atmospheres. And I'm going to right away convert this to kPa for my R value. So atmospheres divide out, kPa, 100 kilopascals in 1 atmosphere. So atmospheres divide out, 100 times 0.75 is 75 kilopascals. All right, so let's see, what else do I know? I know temperature, so 28.5 degrees Celsius. Oops, T equals. We have to add 273 to get our Kelvin temperature. So this is 301.5 K. Let's see, and we also know R. We always know R. R is 8.31 joules per mole Kelvin. And we're solving for V. So, going to my equation, pressure times volume equals moles times R times temperature. I need to solve for V, so I'm going to divide both sides by pressure to get V alone. So volume equals nRT all divided by pressure. So now I can plug my numbers in. So 1.23 moles times my R, 8.31 joules per mole Kelvin, times my temperature, 301.5, all divided by a pressure of 75 kilopascals. So unit-wise, you'll see moles divide out, you'll see Kelvin divides out, and joules and kilopascals, well, a joule is a kilopascal times a decimeter cubed. So this part of it cancels. You're left with decimeters cubed, which is a unit for volume. So it works out. So typing this in your calculator, your answer should have 2 sig digs, right? Because this 75 has 2 sig digs. Okay, so I type it in. I'm going to round it to 41. And that's the volume of the hydrogen gas.